So now we were able to find the inverse of a matrix using two methods, that is using elementary row operation, such that in Gauss-Jordan elimination, okay, or we perform the elementary row operation um, such that we come up with the reduced row echelon form. And then we also had the formula for a 2 by 2 matrix wherein we use that formula to find the inverse of a 2 by 2 matrix. Now, what about systems of equation? How do we apply the matrix inversion in solving the system of equation? According to theorem 2.11, the system of equation with unique solution tells us that if A is an invertible matrix, then the system of linear equation AX equals B has a unique solution X equals to, which is equal to the inverse of A times B. Example, use an inverse matrix to solve each system. So what do? First of all, we find the coefficient matrix, right? So the first thing that we need to do is to find the coefficient matrix. We will have here 2, 3, 2. You have 3, 3, 4. And then you have 1, 1, 1. And adjoin it with the identity matrix. And then you perform the operation, elementary row operation, until the left side matrix, okay, is transformed into I if it is invertible, so that the adjoint matrix is the inverse of your matrix A. So once you're able to find the inverse, you can just use that one to solve for XYZ to be equivalent to your inverse of a matrix. Okay, to find your, the solution X given by XYZ will be equivalent to the inverse of A multiplied to B. So we will have here your inverse of A. So, and it's going to be a 3 by 3 matrix. So let's say we will have here, let's assign the inverse as having, say, C11, C12, C13, then C21, C22, C23, C31, C32, and C33. Multiply it with the entries in B, which is -1, 1, and -2. So since we have a 3 by 3 multiplied by a 3 by 1, the result should be a 3 by 1, which is your X, Y, and your Z. Okay? So this will be your solution to your system of equation by applying your matrix inversion. Okay? So let us see whether um, A will be invertible. So again, we will have your 2, 3, 2, 3, 3, 4, 2, 3, 2, 3, 3, 4, and then 1, 1, 1. Using Gauss-Jordan elimination, that is after applying this one using the elementary row operation, you can solve for the inverse of a matrix. And since you're able to find that one, okay, then we use the inverse of A, multiply that with your B, we come up with the solution 2, -1, -2. Okay, and this is the same process for B. And for C, notice that the matrix A is still invertible, but since the system of equation is homogeneous, okay, then the only solution is the trivial solution, that is your 0, 0, and 0. Okay, so for today, we were able to make use of the matrix inversion process in solving for the system of equation. We learned that to find the inverse of a matrix, we can simply apply the elementary row operations, just like how we use it in Gauss-Jordan elimination. And for a 2 by 2 matrix, there is a specific formula in finding that one, wherein you have 1 over the quantity AD minus CB multiplied by the matrix where you interchange, say, A with D and apply the sign to B and apply the sign opposite to your B and C. Also, we discussed some basic properties on matrix inverses. B.